Welcome to the Fall Asleep Fast channel. On this night, when the stars are whispering, allow me to use this bedtime science video to lay out a cosmic blanket for you now. Please close your eyes and imagine we are riding the moonlit boat of an astronomy bedtime video, drifting in the cradle of the Orion Nebula. Those twinkling stars are not distant scientific symbols, but a customized lullaby of constellations just for you. The heartbeat of Betelgeuse transforms into pulsating rhythms. Jupiter's clouds swirl with milky light vortices, and Saturn's rings sing billions of ice crystals into a cosmic cradle song. The acceleration of the Milky Way's rotation syncs with your breath, and the dust left behind by supernovae reconstructs into the fabric of dreams during meditation. We are no longer mere observers, but stardust floating in the afterglow of creation, letting Einstein's curvature of space-time gently envelop your weary neurons. As the Pleiades bloom with blue light in your mind, allow the boundaries between scientific principles and dreams to dissolve tonight. There is no need to ponder the singularity of black holes. Simply let the waterfall of light from the Andromeda galaxy wash away the day's distractions. For all unsolved mysteries will transform into metaphors for slumber within the starlit cushions of the sleepy science channel. Good night, dear cosmic wanderer. May this bedtime science video escort your consciousness into a sweet dream, more serene than dark matter. Why is the Andromeda galaxy considered the key to humanity's formal exploration of the universe? The Andromeda galaxy is the largest galaxy in the local group, spanning to 120 light years and containing approximately 1 trillion stars. Could such a vast galaxy give rise to a civilization like our own? Next, you will travel to 0.5 million light years on a journey through the Andromeda galaxy. We hope this video brings you a physically and mentally pleasurable interstellar trip. For most of human history, the Andromeda galaxy appeared to us as nothing more than a faint, blurry patch of light in the night sky. You might find it hard to imagine that as recently as the early 20th century, just 100 years ago, scientists were fiercely debating whether it was a nebula or a galaxy. It wasn't until 1924 that a man named Edwin Hubble, using the premier 100-inch telescope at the Mount Wilson Observatory in California at the time, finally uncovered the truth when he calculated that the Andromeda galaxy was located over 2 million light years away. Our understanding of the universe was utterly revolutionized. It was from that moment we truly realized that the Milky Way was no longer the entirety of the universe. It was merely an ordinary member among countless galaxies, each containing billions of stars. From then on, the island universe concept, once a bold idea, was no longer just a theory, but became a reality before our eyes. Later, through calculations, astronomers predicted an even grander future. Our Milky Way and the Andromeda galaxy are inevitably moving towards each other, destined to perform a magnificent cosmic dance billions of years from now, eventually merging into a completely new entity. So what other secrets lie hidden deep within this superneighbor? Among its trillion stars, are there also intelligent eyes gazing back at us? One day in the future, could we or they cross the vast, empty void between galaxies to reach each other's starry seas? The Andromeda galaxy can be said to be one of the most thoroughly studied galaxies to date. Upon entering the Andromeda Galaxy, you would find it both similar to and different from our Milky Way. It similarly contains young blue giant stars and ancient red dwarfs. Its bright core is packed with older red stars, clearly a place with a long history. But in its spiral arms, there are dense gases and dust, serving as stellar nurseries where countless hot blue stars are continuously being born. You see, a galaxy filled only with old stars means it has long ceased forming new stars, while one brimming with young stars suggests it is still in its early developmental stages. The Andromeda Galaxy happens to be a mix of both, indicating it has experienced periodic cycles of star formation, sometimes experiencing a starburst, other times quieting down. What drives these cycles are the motion and interactions of gas, as gas is, after all, the raw material for new stars. The vast reserves of gas and dust within the Andromeda Galaxy also provide clues for understanding its ongoing evolution. Hydrogen, the most abundant element in the universe, constitutes most of the gas here. Vast clouds of hydrogen float between stars, sometimes gathering in dense regions where gravity causes matter to accumulate. If enough gas gathers together, pressure and temperature rise until nuclear fusion ignites and a new star is born. In some places, even entire star clusters are born from a single massive gas cloud. But interestingly, the motion of some gas here is strange, out of sync with the galaxy's overall rotation. This is actually evidence of its past meals. Yes, the Andromeda Galaxy has cannibalized smaller galaxies. When a small galaxy ventures to close, Andromeda's gravity pulls it in, stripping away its stars and gas and incorporating them into its own structure. The faint stellar streams and disrupted gas patterns we see today are the scars left by these past collisions. However, what truly dominates all this is something we cannot see or touch: dark matter. It neither emits nor reflects light, but we suspect it constitutes the majority of the Andromeda Galaxy's mass. How did astronomers first suspect its existence? By studying how the galaxy rotates. Normally, stars and gas at the edge of a galaxy should rotate slower than those near the center, just as planets farther from the sun in our solar system move slower. But observations show that stars in the outer regions of Andromeda rotate almost as fast as those near the core. The only explanation is that some unseen mass provides extra gravity, holding these stars firmly in place. By studying the motion of stars and gas, scientists estimate that dark matter in the Andromeda Galaxy far outweighs normal matter. The stars, gas, and dust we can see constitute only a small fraction of the galaxy's total mass. The rest is locked within this invisible component, forming a massive halo extending far beyond the galaxy's main disk. This dark matter acts like a cosmic scaffolding, shaping the growth and evolution of galaxies. Yet, despite decades of research, its exact nature remains a mystery. Let's look at the specific structure of the Andromeda Galaxy. It includes a bright central bulge, a thick stellar disk, and extended spiral arms. At its very core, it's densely packed with older stars surrounding a supermassive black hole. This black hole has a mass millions of times that of the Sun, but strangely, it doesn't seem as active as some other celebrity black holes in different galaxies. It isn't actively consuming much material and therefore doesn't produce powerful jets or intense radiation. Extending outward from the core, the thick stellar disk spreads across a vast area. The spiral arms curve outward in a familiar pattern, but it's important to know these arms aren't solid structures. They are more like density waves generated by gravity, similar to ripples on water. When these waves sweep through gas clouds, they trigger bursts of new star formation over time. The shape of these arms is constantly influenced by the gravitational pull of dozens of small satellite galaxies orbiting Andromeda. Many of these satellite galaxies, such as the familiar M32 and M110, are being slowly torn apart by Andromeda's gravity. Some of them will eventually merge completely, contributing their stars and gas to Andromeda's ever-growing family. The Andromeda Galaxy also possesses a large number of globular clusters. These dense spheres of tightly packed stars orbit the central region. They contain some of the oldest stars in Andromeda and can be considered living fossils from the galaxy's early era. Studying these clusters provides valuable insights into how galaxies form and evolve, as they are ancient records of the conditions in the universe billions of years ago. Recent research on the Andromeda Galaxy has revealed more unexpected features. For instance, astronomers discovered a vast, thin plane of dwarf galaxies orbiting the main galaxy in a coordinated pattern. This discovery directly challenges our current theories about how galaxies form. Why they are arranged this way is still unclear, as simulations suggest satellite galaxies should be randomly distributed, not neatly aligned in a plane. Another surprising finding is that the Andromeda Galaxy experienced at least one major merger event in its past. While our Milky Way grew mainly by consuming small galaxies, Andromeda seems to have collided with a larger system at some point in its history. This ancient merger completely reshaped its structure, scattering stars and gas everywhere. Evidence of this event is hidden in the motion of stars within Andromeda's outer halo, where remnants of a vast galaxy still linger. So you see, as the closest large galaxy to the Milky Way, the Andromeda Galaxy is like a cosmic laboratory full of puzzles. It gives us the opportunity to understand the workings of galaxies. Scientists are still working to figure out how its supermassive black hole influences surrounding stars, how its satellite galaxies interact with it, and future new telescopes and instruments will undoubtedly provide deeper perspectives, allowing us to map this neighbor in greater detail than ever before. Just as a forensic scientist studies evidence at a crime scene, astronomers can analyze the light from the Andromeda Galaxy to determine the elements that make up its stars, gas, and dust. This chemical fingerprint is unique, shaped by billions of years of stellar evolution, collisions, and the cycle of cosmic material. We know the most common elements in the Andromeda Galaxy are, like elsewhere in the universe, hydrogen and helium-hydrogen. The simplest and most abundant element is the primary fuel for star formation. Helium also exists in abundance, produced in the earliest moments of the Big Bang. These two elements form the basic building blocks of stars, but what truly makes the Andromeda Galaxy chemically distinct are the heavier elements forged over billions of years. within the hearts of its stars as stars live their lives. They create new elements through nuclear fusion. Lighter elements like carbon, nitrogen, and oxygen form in smaller stars, while heavier elements like iron, nickel, and gold are born in more massive stars and supernova explosions. These newly formed elements are released into space when stars die, mixing into the surrounding gas and dust. This cycle continues as new generations of stars form from this enriched material. Thus, the chemical composition of each stellar generation is slightly different from the last. The chemical diversity within the Andromeda Galaxy isn't uniformly distributed. In the galaxy's halo, ancient stars formed billions of years ago contain fewer heavy elements because they were born too early, before many heavy elements had accumulated in the universe. In contrast, the spiral arms, where new stars continuously form, are metal-rich. Astronomers call all elements heavier than helium metals. One of the most striking chemical features of the Andromeda Galaxy is its anomalous isotope ratios. Isotopes are simply different versions of the same element, having the same number of protons but different numbers of neutrons. Isotopes of elements like oxygen and carbon and provide valuable clues about the processes that shaped the galaxy. When scientists compare Andromeda and the Milky Way, they find differences in these isotope ratios, hinting that the two galaxies might have followed very different evolutionary paths. These differences can be traced back to which types of stars contributed most to Andromeda's chemical makeup. Some isotopes are produced in the intense heat of massive stars, while others form in slower-burning, lower-mass stars. By analyzing the distribution of these isotopes, astronomers can determine which stellar types play the leading role in shaping Andromeda's chemistry. The patterns they observe suggest that, compared to the Milky Way, Andromeda may have experienced different rates of star formation or even different types of stellar explosions. When one galaxy merges with another, it doesn't just absorb stars, it also incorporates any unusual chemical signatures the other carries. Some outer regions of Andromeda show elemental signatures inconsistent with the typical composition of the main disk. These are likely traces left by galaxies long gone, absorbed by Andromeda, preserving their unique chemical imprints. Compared to the surrounding regions, the galaxy's core contains higher concentrations of iron and other heavy elements. This suggests that Andromeda's core might have experienced periods of very intense star formation and supernova activity in the past. Some of these elements were likely produced in short-lived, massive stars that exploded violently, polluting the surrounding space with heavy elements. This process is similar to what we see in other galaxies with active star-forming regions. Some studies also suggest that, compared to galaxies of similar size and age, the abundance of certain elements in the Andromeda Galaxy, such as magnesium, seems slightly lower. This could be a signal that Andromeda's chemical evolution was influenced by external factors, such as changes in its early environment or past interactions with other galaxies that altered its star formation history. Dust composed of tiny solid particles of carbon, silicon, and other elements is scattered throughout the galaxy. Don't underestimate this dust. It plays a crucial role in the formation of new stars and planets, as it provides the raw material needed to build planetary systems. The chemical composition of this dust varies across the galaxy. Some regions are richer in carbon-based grains, while others are dominated by silicates, similar to rocky substances on Earth. One of the key tools scientists use to analyze Andromeda's chemical fingerprint is spectroscopy. By studying the light emitted or absorbed by different elements, astronomers can determine the precise composition of the galaxy. This technique has also helped detect the presence of molecules like carbon monoxide, which are typically found in dense clouds where new stars are forming. Detecting these molecules helps us understand how the Andromeda galaxy continues to evolve and produce new generations of stars. As the Andromeda galaxy continues to form stars, its overall metallicity, the abundance of elements heavier than helium, will increase. However, as its primordial gas supply slowly depletes, the rate of star formation will eventually decline. Ultimately, the Andromeda galaxy will become a galaxy dominated by old stars, with fewer and fewer new stars being born. And when it finally merges with the Milky Way in about 4 billion years, this newly merged galaxy will carry the chemical fingerprints of both systems, fusing their histories into a brand new cosmic identity. The Andromeda galaxy is home to a vast variety of stars, many following familiar life cycles similar to those we see in other galaxies. Yet, among these ordinary stars, there are also rare and unusual luminaries scattered about. Some are remnants of violent cosmic events, while others are still forming in ways that challenge our current models of stellar birth. One of the most captivating rare stars in Andromeda is the luminous blue variable. These are massive, temperamental stars prone to sudden changes in brightness. They dance on a tightrope between gravity and radiation pressure, often shedding their outer layers through intense stellar winds. The most famous one in Andromeda, Andromedae, fluctuates in brightness constantly. We believe these stars are in a very brief evolutionary phase, soon to explode as supernovae, making them key targets for understanding the final fate of massive stars. Scattered within Andromeda's spiral arms are also many Wolf-Rayet stars. These are rare, extreme, hot, massive stars nearing the end of their lives. They have shed most of their outer hydrogen, exposing the hotter, deeper layers where heavier elements are being formed. Consequently, they emit intense stellar winds and shine with a piercing blue-white light. Their presence indicates recent star formation activity in the region, as they live only a few million years before collapsing in spectacular supernova explosions. Then there are Andromeda's hypervelocity stars. These stars move at extraordinarily high speeds, seemingly impossible under normal circumstances. Some may have been kicked out of binary systems when their companions exploded as supernovae. Others might have been slingshot after a close encounter with Andromeda's supermassive black hole. These hypervelocity stars move so fast that some might eventually escape the galaxy entirely, forever wandering through the void, carrying clues about the extreme gravitational forces within Andromeda. Lurking in the galaxy's outer regions is another type of rare star, the carbon star. These stars have an unusually high abundance of carbon in their atmospheres, giving them a distinct reddish glow. We believe carbon stars result from convection within the star dredging up carbon from deeper layers, enriching the outer atmosphere. This process changes how the star emits light, making it appear redder than ordinary stars. Andromeda's carbon stars are particularly interesting because they hint at how chemical elements are recycled within the galaxy. These stars expel carbon-rich material into space, providing valuable raw material for future star and planet formation. Deep within Andromeda's central bulge, astronomers have also discovered a population of unusual, extremely metal-poor stars. These stars formed early in the galaxy's history when heavy elements were very scarce. They are relics from a younger universe. Their composition allows us a glimpse into conditions billions of years ago, containing very few heavy elements. They are considered among the oldest stars in Andromeda, possibly dating back to the galaxy's very formation. There are also yellow supergiants, stars in a brief transitional phase from red supergiants to blue supergiants. This makes them rare and difficult to observe. Yellow supergiants are rare precisely because this evolutionary stage lasts only a few thousand years. A mere blink in cosmic time, their presence in Andromeda provides crucial data on the life cycles of massive stars, helping astronomers refine models of how these stars change over time. Perhaps one of the strangest stellar categories in Andromeda is the magnetar, a neutron star with an incredibly powerful magnetic field. These remnants of collapsed massive stars emit bursts of high-energy radiation. Their magnetic fields are trillions of times stronger than Earth's. Detecting magnetars in Andromeda indicates that this galaxy has experienced numerous supernova explosions, each potentially leaving behind such a highly magnetized monster. Studying these objects helps us understand extreme physics in ways impossible to replicate in earthly laboratories. Finally, there are variable white dwarfs. These are the small but dense remnants of dead stars, sometimes showing unexpected brightness variations, possibly due to pulsations or interactions with surrounding matter. Unlike more common white dwarfs, these rare versions might be part of binary systems, slowly stealing material from a companion star. In some cases, this process can lead to a sudden thermonuclear explosion on nova, temporarily increasing the white dwarf's brightness thousands of times before it fades again. Each new observation enhances our understanding of how stars evolve, how galaxies change over time, and how different cosmic environments affect stellar life cycles. These hidden giants, though often overlooked in broader galactic discussions, provide crucial clues to Andromeda's past and future, reminding us that even in a well-studied galaxy, countless mysteries remain to be unraveled. The Andromeda Galaxy, of course, is not merely a collection of isolated stars. It's more like a vast cosmic landscape where stars prefer to cluster together, forming co-evolving communities within star clusters. These clusters range from dense and ancient to loose and relatively young. One of the most striking types of star clusters in Andromeda is the globular cluster. These dense, spherical groups of stars are among the oldest structures in any galaxy, typically containing stars formed early in cosmic history. Andromeda boasts far more globular clusters than our Milky Way, with estimates of over 500 orbiting it. But interestingly, some of these clusters seem different from those typically seen in other galaxies. A few contain stars much younger than expected, raising questions about their formation. Others appear to have unusual motions, suggesting they might not be native to Andromeda, but were captured from smaller galaxies during past collisions. Astronomers have also found a surprising number of extended clusters in Andromeda. These stellar groups are less dense than traditional globular clusters, but still gravitationally bound. They are unusual because they blur the line between star clusters and small galaxies, and like the tightly bound, relatively spherical typical globular clusters, extended clusters have a more dispersed structure and lower overall density. Some scientists believe these objects might represent a transitional stage between star clusters and dwarf galaxies, offering a rare glimpse into how galactic structures evolve over time. Andromeda also hosts a particularly mysterious type of cluster called faint fuzzies. Initially identified in Andromeda's outer regions, they don't seem to fit neatly into either the globular or open cluster categories. They contain old stars similar to those in globular clusters, but have a looser structure, making it unlikely they could have survived for billions of years without gravitational disruption. Some theories suggest they might have originated from a merger between Andromeda and a small galaxy long ago, leaving behind these remnants that are slowly dissipating over time. Andromeda also possesses an unexpectedly large number of young, massive star clusters containing bright, hot stars only a few million years old. The existence of these young clusters is surprising because many are found in regions where star formation was thought to have largely ceased. Some are located far from Andromeda's main star-forming regions, leading to speculation that their formation might have been triggered by tidal interactions or past collisions with satellite galaxies. The chemical composition of some clusters also doesn't match the rest of the galaxy. Some contain stars with unusual metal ratios, and a few even have compositions more typical of dwarf galaxies than large spiral galaxies like Andromeda. This suggests that Andromeda has been absorbing smaller galaxies, and their clusters have naturally become part of its stellar population. Studying these clusters provides evidence for Andromeda's merger and accretion history, allowing astronomers to reconstruct past events that shaped the galaxy's present appearance. The distribution of clusters also poses puzzles. Some are found in locations where they should have been torn apart by gravity long ago, while others form patterns suggesting they might have originated from larger structures. Some clusters even appear aligned into streams or arcs, possibly remnants of past mergers. These patterns indicate that Andromeda's halo is still being shaped by ongoing interactions with smaller galaxies. Some of the overlooked clusters in Andromeda are even harder to classify. A few seem to contain extremely massive stars that shouldn't have survived for billions of years. Others contain an unusual mix of stars, some appearing much younger than expected. These anomalies lead to speculation that some clusters might be only temporary, loosely bound by gravity, destined eventually to dissipate into Andromeda's general stellar population. Advanced telescopes have also revealed more clusters hidden near the galaxy's core in dense regions previously obscured by dust and bright starlight. These central clusters might hold clues about Andromeda's central supermassive black hole, possibly interacting with its powerful gravity. Other discoveries include clusters located extremely far from the galaxy, raising new questions about how far Andromeda's influence extends into intergalactic space. At the heart of the Andromeda Galaxy lurks one of its most powerful features, a supermassive black hole. This colossal object, hidden deep within the galactic core, influences everything around it. It shapes the motion of stars, bends light, and devours any matter that ventures to close. Scientists long suspected that most large galaxies harbor such black holes at their centers. Observations showed that Andromeda's supermassive black hole, designated M31*, has a mass approximately 140 million times that of the Sun. This makes it much larger, and the black hole, the center of our Milky Way, Sagittarius*. The presence of such a massive object at Andromeda's core naturally raises questions about how it formed and grew to its current size. Some theories suggest that as Andromeda absorbed smaller galaxies over billions of years, each swallowed galaxy brought its own black hole. These black holes eventually merged at the center, forming a single, more massive black hole. Surrounding M31* is a dense cluster of stars, a distinctive feature that sets it apart from some other galactic centers. These stars move at incredible speeds under the immense gravity of the black hole. Observing these motions helped astronomers confirm the black hole's existence, as only such an extreme concentration of mass could explain the star's behavior. Unlike some other galaxies, M31* does not currently appear to be feeding heavily. Many central black holes in galaxies form active galactic nuclei, where gas and dust swirl around them, heating up and producing powerful radiation. However, Andromeda's black hole is relatively quiet, emitting only small amounts of X-rays and radio waves. Scientists believe this might be just a temporary phase. In the past, this black hole might have been more active, accreting matter and releasing energy, thereby shaping Andromeda's core. Future collisions with gas clouds or even entire stellar systems might reawaken it, making it a more active and dynamic feature of the galaxy. In addition to this central behemoth, the Andromeda Galaxy might contain smaller, intermediate mass black holes scattered throughout its structure. These black holes, with masses ranging from hundreds to thousands of times that of the Sun, are thought to form from collapsed massive stars or through the merger of smaller black holes. While the supermassive black hole dominates the galactic center, intermediate mass black holes remain elusive and are among the hardest astronomical objects to detect. Some might be hiding within the dense star clusters orbiting Andromeda. There is growing evidence that the centers of some globular clusters might also harbor black holes, influencing the motion of surrounding stars. If confirmed, these intermediate mass black holes could help explain how supermassive black holes grow over time. Some scientists even suggest that certain clusters in Andromeda might contain multiple black holes, creating complex gravitational interactions that could eventually lead to the formation of a larger black hole through repeated mergers. There are also rogue black holes that don't stay in a fixed location, but drift throughout the galaxy. These might have formed during past galactic collisions, ejected from their original positions by powerful gravitational forces. Some could be remnants of smaller galaxies consumed by Andromeda in the past. Black holes themselves are extremely difficult to detect unless they are interacting with nearby matter. However, their gravitational influence can sometimes be observed. When they pass in front of a distant star, they briefly bend and amplify as light, a process known as gravitational lensing. Though invisible, these objects exert powerful gravitational forces that can influence star formation, disrupt planetary systems, and even alter the paths of entire star clusters. If Andromeda does contain a significant population of these hidden black holes, they could play a considerable role in its evolution. Gravitational wave detectors capable of sensing ripples in space-time might also help us identify hidden black holes within Andromeda in the future. As technology advances, astronomers will be able to explore these mysterious objects in greater detail, revealing more about their origins and their impact on the galaxy. It is this mysterious dark matter, constituting over 90% of the Andromeda galaxy's mass, that acts like an invisible giant hand, not only shaping the galaxy's grand structure, but also determining its fate and that of its neighbors. To unveil its secrets, astronomers employ telescopes across the spectrum from optical and infrared to radio, combined with powerful computer simulations, piecing together a detailed map of this 220,000 light-year-wide stellar sea like a complex jigsaw puzzle. Of course, the vast distance and immense size also mean many mysteries persist. We still know very little about certain regions of the galaxy. Future discoveries will require new technologies to unveil their secrets. The Andromeda Galaxy is not a lonely monarch. Its throne is surrounded by dozens of humble vassals, those smaller satellite galaxies. But this is not a peaceful coexistence. It's a cosmic feast that has lasted for billions of years. The Andromeda Galaxy can be described as a cold-blooded devourer. Within its gravitational web, some satellite galaxies have already been torn apart, leaving behind debris like M32 and M110 clinging closely to their master. Others are caught in a death spiral, stretched into stellar streams hundreds of thousands of light years long, like cosmic scars silently narrating the violent process of being consumed. These stellar streams are direct evidence of the Andromeda Galaxy's continuous expansion and growth into such a massive entity. Even more astonishingly, these satellite galaxies are not randomly distributed, but are eerily aligned in a vast plane, as if following some cosmic rule we have yet to understand. This remains a major astronomical mystery in this gravitational tug-of-war. Even dark galaxies, composed almost entirely of dark matter, have been born. These ghosts of the cosmos contain very few stars yet possess immense mass. The fate of these satellite galaxies is already sealed. Either be completely consumed and become part of Andromeda, or be flung into the endless void of intergalactic space. The unbridled growth of the Andromeda Galaxy is evident not only in its consumption of neighbors, but also in the creation of a magnificent stage of death and rebirth within its confines. Here, the death of stars is the most splendid firework display in the cosmos. Supernova explosions, each one scatters heavy elements essential for life, like carbon, oxygen, and iron, into interstellar space, becoming the seeds for future planets and life. We can even see the ghostly echoes of a supernova explosion that occurred over 100 years ago, still whispering near Andromeda's core. The shockwaves from these explosions act as cosmic plows, tilling gas clouds and igniting the birth of new stellar generations. The surviving stars are not static either. Thousands of variable stars act like the beating heart of the Andromeda Galaxy. The most famous among them, Cepheid variables, with their precise rhythms, serve as our cosmic measuring tape for gauging this distant stellar sea. Other variable stars, through the dance of eclipsing binaries or sudden energetic outbursts, reveal secrets about stellar life cycles previously unknown. It is the deathly echoes and vital pulses of these stars that together compose the grand and dynamic symphony of the Andromeda Galaxy. Yet, when we listen carefully to the grand movements of this symphony, we find its melody is not perfectly harmonious. Viewed from afar, the iconic spiral arms of the Andromeda Galaxy are full of perplexing flaws. It doesn't possess the smooth, symmetrical, elegant curves of textbook spiral galaxies, but it exhibits a chaotic beauty. We can see two or even multiple spiral arms strangely overlapping, as if two paintings were forcibly superimposed. Its spiral arms are sometimes bright and dense, other times faint and sparse, filled with breaks and gaps. Beyond the main arms float faint stellar rings and filamentary structures. All these irregularities are not design flaws, but direct witnesses to its wild history. Each act of consumption, each collision, has left an indelible mark on its structure. The warped, asymmetrical arms we see today are the scars left by billions of years of gravitational warfare. They reveal an Andromeda Galaxy more ferocious and dynamic than we ever imagined. In this ferocious, dynamic sea of stars, what will be the fate of planets? Could there be another Earth there? This is the ultimate goal of our exploration, the search for exoplanets. Due to the extreme distance, traditional methods are ineffective, but astronomers are using a clever technique, gravitational microlensing, treating the stars of the Andromeda Galaxy as natural magnifying glasses to capture the faint flicker produced when a distant planet passes by. We can be almost certain that among its 1 trillion stars, countless planetary worlds are hidden. Some might be similar to Earth, peacefully residing within the habitable zone. Others, in the galaxy's wild history, might have been ruthlessly ejected, becoming rogue planets drifting alone in the darkness. Although we cannot yet see their details, each observation brings us closer to confirming the first planet in Andromeda and to answering that ultimate question: are we alone? Since we can see worlds there, can we reach them? The answer is brutal. With our current fastest probes, traveling to the Andromeda Galaxy would take over 4 billion years. This is a despairingly vast distance, but human imagination has never been bound by distance to cross this cosmic ocean. Scientists have conceived various incredible schemes: laser-pushed light sails, ultimate engines fueled by antimatter, even warp drives that distort space-time itself, and wormholes connecting to points in the universe. However, even if we solve the speed problem, the real test has just begun. During a voyage lasting millions of years, lethal cosmic radiation, irreparable mechanical failures, and eternal loneliness are nightmares travelers must face. This journey would either require world ships capable of supporting generations in a self-sustaining environment or rely on self-replicating, tireless AI robots to complete this ultimate exploration on our behalf. Although all this seems like unreachable science fiction today, who can say that in the distant future, humanity won't truly set sail for that starry sea to 0.5 million light-years away? Perhaps we don't need to travel that long, because a more certain future is rushing towards us at 110 kilometers per second, and for 0.5 billion years, the Milky Way and the Andromeda Galaxy will meet head-on. This won't be an instantaneous collision, but a magnificent and chaotic cosmic dance lasting billions of years. In this dance, the familiar spiral arms of the Milky Way and Andromeda will be mercilessly torn and stretched by gravity into vast tidal tails spanning the heavens. Compressed gas clouds will trigger an unprecedented frenzy of star birth, lighting up the entire night sky with countless newborn blue stars. So what will happen to our solar system within this maelstrom? Fortunately, the distances between stars are immense. The probability of a direct collision between the solar system and another star is extremely low, but we are not entirely safe. The entire solar system would be gravitationally flung into a completely unfamiliar corner of the new galaxy, or even ejected entirely, becoming a lonely ghost in intergalactic space. The core spectacle of this collision will occur at the centers of the two galaxies. Andromeda's supermassive black hole, dozens of times more massive than ours, will engage in a death waltz with the Milky Way's black hole, eventually merging into an even more colossal space-time monster, becoming the absolute master of the new galaxy, Andromeda or Andromeda. At that time, the old cosmic order will completely dissolve, and a new, more massive elliptical galaxy will be born from the chaos. This is our shared destiny with the Andromeda Galaxy. Facing such a grand future, how can we explore this neighbor more deeply? The answer lies in the light beyond what our naked eyes can see. First, infrared light. It can penetrate the thick cosmic dust of the Andromeda Galaxy, allowing us to see secrets hidden beneath visible light. Stellar nurseries, the warm afterglow of aging stars, and the true face of the galactic core, often masked by bright light. Next, we use radio waves to listen. Through them, we can not only map Andromeda's vast hydrogen reserves, its invisible body extending far beyond its visible form, but also catch the rhythmic signals from pulsars and even attempt to search for potential artificial communications, hoping one day to hear a greeting from another civilization. Most ingeniously, we can even use the Andromeda Galaxy itself as a giant cosmic magnifying glass. Utilizing the gravitational lensing effect caused by its powerful gravity warping space-time, we can not only glimpse more distant, ancient galaxies from the universe's infancy behind it, but also detect the faint flicker caused by rogue planets or black within it passing in front of background stars. But observation alone cannot satisfy us. If we truly wish to reach Andromeda, mere flight is insufficient. Therefore, physicists are looking to the limits of theory. Wormhole theoretical shortcuts connecting to points in space-time, if they exist and could be stabilized, would reduce intergalactic travel from millions of years to an instant. Although this remains theoretical, It represents the ultimate romance and ambition of human exploration, and the ultimate goal of this romance and ambition has always been to answer the oldest question: does life exist in the Andromeda Galaxy? Although we cannot directly see planets there, based on our understanding of life, we can make some educated guesses. There are abundant heavy elements, stable stellar systems, and even potential refuges for life in the subsurface oceans of icy moons. More importantly, we should not be constrained by Earth's template. Life might exist in forms we cannot even imagine, silicon-based or other configurations. If life has evolved, what heights might intelligent civilizations reach? This leads to the contemplation of alien megastructures. Could a civilization millions of years older than ours build Dyson spheres enveloping entire stars to harness energy, or stellar engines capable of moving entire galaxies? By listening for whispers from Andromeda with radio telescopes, we are searching for potential traces of such cosmic marvels. When we turn our gaze from them back to us, an even bolder plan emerges: the Andromeda Initiative. This isn't merely about travel, but a blueprint for interstellar colonization concerning humanity's future. It envisions sending self-replicating AI robots as pioneers to establish outposts, followed by humans traveling in multi-generational world ships, or perhaps via mind uploading, sowing the seeds of our civilization in another galaxy. This represents the ultimate dream of humanity transitioning from a planetary species to an interstellar one. Of course, whether searching for life or speculating about the future, we must acknowledge that the Andromeda Galaxy still holds too many unsolved mysteries. From its peculiar dark matter distribution to its extraordinarily large black hole, each mystery is a new starting point driving our continuous exploration. It is these knowns and unknowns that constitute the endless charm of the Andromeda Galaxy. It is not merely a distant point of light, it is a mirror of our cosmic understanding, reflecting our past and foretelling our future. It makes us constantly question, constantly explore. All right, my friend, let's conclude our conversation here for tonight. Now, allow me to press pause for you. Set aside all thoughts and inquiries, and simply be present in this moment. From here, my words will fade away, leaving only the silent tapestry of the cosmos and a carefully curated piece of pure music tuned to 430 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into a state of deep relaxation. Now, find your most comfortable position. Gently close your eyes, or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night and sweet dreams until we meet again among the stars.